if you're going to make an argument against me about how AIs are meeting and surpassing their benchmarks, well, I have a study for you. Assessing and advancing benchmarks for evaluating large language models in software engineering tasks. So essentially what they did is, this is a meta study, I guess if you want to call it that, although you can't really call it that. They took 291 benchmarks, which are used to benchmark how well an LLM does. So for all the benchmark bros who are coming at me going, well, but these things pass their benchmarks, we're going to look at what these benchmarks actually contain. And this is a more critical view of these benchmarks. So I'm going to jump ahead to some sections because, again, I've read this one in full, and these are the points that stand out to me the most. So it doesn't honestly really matter the type of benchmark. There are different types of benchmarks that benchmark for different kinds of things, including code-based ones, but they covered several. So let's see what they found as some of the limitations of these benchmarks, because that's essentially what they were going into it with. Are there limitations to these benchmarks? How accurate can these benchmarks, or how much can these benchmarks be trusted? So here's the first one: lack of sufficient benchmarks. Since software requirements are confidential assets of a company, it is difficult for typical researchers to access actual software requirements. So you can imagine a benchmark being generated for an LLM based on some requirements where you do not know the actual requirements in real life. You have to make them up. Many current studies related to RE still focus primarily on using software requirements constructed a long time ago, and we're talking in some cases software requirements coming from 10 to 20 years ago, such as those from Promise and Pure. However, these ubiquitous RE benchmarks on one hand cannot comprehensively evaluate the performance of LLMs, and on the other hand may not represent real industrial data. So on the one hand, you can't have a good evaluation of LLMs, and you can't even represent real data. So it's bad in two ways. Challenges in creating a unified benchmark. Well, obviously this is a problem, because how are you going to create a benchmark that asks questions that are requirements of a typical software company that encompasses the vast majority of things you see as requirements in software companies? These things are nuanced. So right at its face, these benchmarks already have a serious problem. They have to essentially be made up in order to get to where they are. Automated code generation and recommendation systems supported by code-related LLMs have become integral. Okay, now, these scenarios, context, which is essentially the ability or the memory for the LLM to put into its memory the context of the code that it needs to tackle and give you an answer on. The domain, which is the problem space that you're trying to solve. And then the task, which is what is the problem, right? So you have to look at the surrounding problems and solutions. You have to have enough memory, and then you have to bring it all in together, into here is the answer. Okay. And so they go into these things, they describe all of this stuff. So these are some of the limitations on these kinds of things. Over-reliance on pass at K and execution-based metrics. So pass at K is an evaluation metric. It honestly doesn't really matter what it is. You can look it up. It's just something that was kind of pulled out of a series of evaluation metrics that have been scientifically studied in the past. And they were, they provided references to them. And this is what these benchmarks adopt as an evaluation metric. It solely measures whether generated code passes a predefined set of test cases. This often overlooks partial correctness, code quality, and semantic nuance, and is sensitive to the number and diversity of test cases, which means in some of these benchmarks, the more test cases you add as part of your benchmarking, the worse the output is. Yeah. Yes. Limited diversity of tasks and contexts. Existing benchmarks predominantly focus on short, isolated programming tasks, for example, function-level Python coding. There is a lack of coverage for real-world software engineering scenarios, such as multi-file projects, GUI or API development, or maintenance-oriented tasks. Insufficient coverage of programming languages and paradigms. Most benchmarks target high resource imperative languages like Python, Java, and C++. Functional, logic-based, and domain-specific languages like Rust, Prolog, and Verilog remain underrepresented, limiting the generalizability of evaluation results. Shallow reasoning and low-level semantics. Benchmarks often fail to capture deeper logical reasoning, algorithmic insight, or mathematical precision. Few benchmarks evaluate symbolic reasoning, problem decomposition, or invariant label noise and ground truth ambiguity. Some benchmarks rely on mined or auto-aligned ground truth solutions, which can be noisy or incomplete. For example, there may be multiple valid implementations for a task, but benchmarks assume a single correct reference or oracle. So you might have something that you can validly accomplish in a variety of different ways, but some benchmarks bring in only one correct way to do it. And then they go pass. Lack of human-centric evaluation dimensions. Code generation quality also involves readability, maintainability, efficiency, and developer satisfaction, which are difficult to capture through automated metrics alone. So this remains unaddressed. Let's keep going. It's not over. Let's go, I think it's 3? Yeah. Continuing the limitations of other types of benchmarking. So some of these benchmarkings are similar in that they consist only of handcrafted programming problems in Python. That's right. And thus cannot be directly used to systematically evaluate the performance of multi-language software testing. In addition, these problems are simple, single-function generation tasks that do not match actual development scenarios. There is a language limitation. Some of these only focus on Java programs. There is a project selection bias. While several of the above benchmarks contain a variety of Java projects, the selection may not cover the full range of real-world applications, including niche ones, for example. Or it may favor well-maintained projects and may overlook more complex and less frequently updated projects. Keep going. A significant issue is the rise of benchmark data contamination, where the overlap between the training data and the test data leads to inflated performance metrics. This is called data leakage. Due to the lack of retraining capabilities and inaccessibility to the pre-training data of many LLMs, it's impossible to determine how much this leakage has an effect on the benchmarks. Despite the fact that we have a vast amount of log data available, existing benchmarks in log parsing, or LLMs parsing logs, typically focus on a limited set of well-known and popular software. In log statement generation, the context window of 512 tokens means that there is a very limited output that these LLMs can give when they are looking at generating logs for you or parsing logs. Let's keep going. There's only a few more on this one. Again, we have data leakage between training data and testing data. So because you cannot retrain it, and you don't have accessibility to the pre-training data, it's challenging to assess the extent of benchmark data contamination. So you don't even know how contaminated these benchmarks are. Then there's the absence of comprehensive measures to evaluate the accuracy of predictions. So kind of describing what it was describing before, which is there are many different factors that have to be evaluated for how well something got generated by an LLM, and it's just not comprehensive enough. Let's go to the last few bits here. I think it's 9.1.4. Yes. Current benchmarks lack diversity in the types of bugs they cover. Data sets exhibit an uneven distribution of bug types and project contexts. A significant portion of existing research is based on a few amount of programming languages. Simplified scenarios are used for testing these benchmarks. Data contamination, vulnerabilities, such as the generation of vulnerabilities by these things, right? So let's go to 9.2.4. Okay, so hang on. The quality of the data, right? So how well was the training data, like how accurate or how well was the training data put? We have no real way to determine that. How well does it represent real world scenarios? It doesn't. Okay, and so this then is the summary of everything they found with these benchmarks. Unclear task definitions. You cannot scale these benchmarks to real-world environments. They are overfitted, which means models overfit tasks in order to get that check mark. There are benchmark updates that have not been updated in a long time. And then there are data concerns like privacy concerns, security concerns, generated code security concerns, etc. So when the benchmark bros come up to me and go, but look at all the benchmarks that these AI systems are passing, clearly this is evidence that AI is going to take out large swaths of the industry. No, it's not. You're buying into hype and marketing material.